Okay, so next up, 55. Which of the following? So we got some naming coming up, and it looks like Lewis structures. But all right, which of the following is the correct name? We always take the compound. First one keeps its name, so sodium. Second one, if there are no polyatomic, so if it's only two elements, gets an ID ending, sulfide. Okay, so sodium sulfide. So we have to make two choices at this point. If it's all nonmetals, as in the first one, it's really the first one. If the first one's a nonmetal, we add prefixes. And we have no nonmetals here. So, or we have sodium, which is a metal. Um, the second thing is if it is not fixed, it's not a fixed charge, it's not always the same, we are going to add Roman numerals. The Roman numeral is the charge of whatever that metal is. And again, the things that are fixed are group one is always +1, group two is always +2. And we look at the staircase. Okay, so aluminum, below that gallium, to the left of that zinc, cadmium, and silver. So if it's one of those also count as fixed. By the way, aluminum and gallium 3 plus, zinc and cadmium 2 plus, and silver 1 plus. So that's the list of fixed. So if it's not one of those, and it's not, it's sodium, or it is, I'm sorry, it's group one. So sodium sulfide, that's the name. Sodium sulfate, that would be with the polyatomic. We're looking for sulfide, that's sulfite, sulfide. So sodium sulfide, D. What's the name for the next one? Okay, first one keeps its name, manganese. Last one gets an IDE ending, oxide. And so now we have to make a decision. Do I have any metal? Do I have any metals? Yes, manganese is a metal. So we are going to add a Roman numeral. What is the charge of this thing? Well, if we look at it, I know oxygen is -2. All of the oxygens together are -14. This whole thing is neutral. So the manganese has to be +14. One of the individual manganese is +7. So manganese 7 oxide is going to be our answer. Manganese 7 oxide. Again, this is the charge of the metal, not how many are present. All right. Which of the compounds is most likely to be covalent? Let's answer this a different way. Which is most likely to be covalent? Which is not ionic? So an ionic compound contains a metal or hydrogen first. That would be, because that's an acid. So a metal or hydrogen first, that makes it ionic. Okay, so rubidium, ionic. Strontium, ionic. Carbon is not a metal, so we're going to call that covalent. And calcium is ionic. There we go. So again, identify the ones that are metals. Which of the following names is not correct? All right, carbon tetrachloride. Do I need a prefix? I don't remember. I don't always have one. So this would be mono, but we never put mono after the first one. Carbon is not a metal, so this name is correct. Carbon dioxide. Again, no mono in the front, di in the second. So carbon dioxide, correct. Nitrogen trihydride. Yep, nitrogen, one nitrogen, three hydrogens. Again, we'd never add mono in the first one. Hydrogen monoxide. Actually have two hydrogens, so this should be dihydrogen monoxide. The only prefix we omit is one for the first one. All right, next up. Which Lewis dot symbol represents carbon? Whenever I'm doing a Lewis dot symbol, so let's just do, I don't know, xenon. This is the order of filling. So group one, you'd have just one dot. Group two, you would have two. And we keep going around and we put one on each side before we start to pair up. Okay, so that is the order of filling. So if we were to do nitrogen, it's got 5. 4, and there's my 5th one. For carbon, it's got 4 valence electrons. 1, 2, 3, 4. There's my 4th valence electron. That's what we're looking for. So this is wrong because it's got too many. This is wrong because they're all paired. This is correct. 3 is correct. Lewis dot symbol to represent fluoride ion. Okay, fluorine has 7, 2, 3, 4, 5, 6, 7. The fluoride ion is plus 1 electron because it's going to come F minus. 1, 2, 3, 4, 5, 6, 7, 8. Goes from 7 to 8. And we always put the brackets around it to represent that this whole thing is negatively charged. So these are not charged. And this is missing an electron. So 1 is correct here. All right, next up. Consider the Lewis dot symbol for oxygen. Okay. 1, 2, 3, 4, 5, 6. How many covalent bonds does it prefer? A covalent bond has 2 electrons in it. So if I have 2 things bonded together, there are 2 electrons there. Generally, what happens is you have 1 electron from one atom, 1 electron from another. They form together to give you a covalent bond. And so when you have, there's 2 types of pairs of electrons or sets of electrons in a dot structure. These are called non-bonding. They're basically just that lone pair. And so they don't form ionic, or they don't form covalent bonds. But a single electron like this is known as a bonding electron. That one is ready to create a bond. And we, in fact, have 2 of those. So we expect oxygen to form 2 bonds. Okay, if we did the same thing for, I don't know, nitrogen. 1, 2, 3, 4, 5. 1, 2, 3. This would form 3 bonds and have 1 lone pair. So that's how we determine how many bonds we expect. How many bonding electrons does it have? All right, the Lewis structure for CS2. Okay, so Lewis structure. So just a quick blurb on Lewis structures. Step 1, count the electrons. So carbon, so CS2, carbon has 4 electrons. There are 2 sulfurs, they each have 6. The total is going to be 16 total electrons for this. Second, we're going to draw a skeleton. The skeleton structure has carbon in the center always, but the thing that's the most electropositive or furthest away from fluorine. So carbon in the center with a single bond to things that are nearby. I just used 2 electrons because I created the bonds here. Okay, so I just used 2 electrons. So 16 minus 4 brings me down to, let me do that properly. 16 minus the 4 electrons from the bonds that I just used brings me down to 12. Next, we're going to take care of the peripheral atoms. I'm going to add electrons. We want to get 8 electrons in that periphery. So all of the peripheral atoms are going to get 8 electrons. So right now, sulfur has 2 electrons in the form of the bond. There's 2 electrons in a bond. So 2, 3, 4, 5, 6, 7, 8. This sulfur is going to be the same. I just used another 12 electrons. I've got no electrons left. Step 4, remaining electrons to the central atom. Okay, we don't have any electrons left. 5, if the central atom is not happy, we need to multiple bond if needed. Multiple bond. Okay, so carbon right now has 4 electrons, so I'm going to get rid of those and put them in a bond between. Get rid of those and put them in a bond between. This is the final Lewis structure of, this is the final Lewis structure for CS2. So that means this one, nope, because we need carbon in the center. It looks like 4, nope. And nope. So 4 it is. Which of these Lewis structures is incorrect? This is going to be the same kind of thing, totaling up the electrons. This one looks correct. This one looks correct. This one looks correct. Nitrogen 2, 4, 6, 8, 10, 12. Nitrogen is in N2, nitrogen is in group 5. 2 times 5 gives me 10 electrons. This one has 2, 4, 6, 8, 10, 12. This one has 12 electrons, though. So this one's incorrect. 4. According to VSEPR theory, so this is geometry. What's the shape of this molecule? So we're going to do the Lewis structure for this. Okay. And so what we find out is this is what PCl3 looks like. And a lone pair there. Let me redraw it so it's a little bit more accurate. These chlorines, this lone pair is up top, this chlorine is down here, and this chlorine goes back. So ultimately what we have is 4 electron groups or domains, depending on how you look at it. 4 electron groups, 3 bonding, 1 non-bonding. So if we look at our table, or if we understand how this works, the electron groups makes it tetrahedral, but we're missing one, we can't see it. So this is trigonal pyramid. This pair of electrons on top is kind of pushing down on the sides, making those chlorines kind of fold down a little bit. So trigonal pyramid for this. All right, according to VSEPR theory, what's the shape of SiCl4? Again, you're going to draw it out. This is 4 electron groups, and they're all bonding tetrahedral. Which of the following species should be linear? So this is just a matter of drawing all of these out, but I'm going to let you do that, looking at VSEPR theory to decide which one is going to be linear. Linear, for something that's linear, we are looking for something with 2 electron groups in the end, right? That's what we're looking for linear. That's the only option that we really have for linear. VSEPR theory. For bent, however, again, we're going to draw these out. There's 2 options that we have. If we have something with 4 electron groups, but it's going to have 2 bonding and 2 non-bonding, that would be bent. The other option is 3 electron groups, 2 bonding, and 1 non-bonding. So those are the options. So I'll let you look through and decide which one it is. Which property is used to determine the degree of polarity? Polarity is measured by electronegativity. So if I have 2 things, so if I have hydrogen, let's say, attached to a fluorine, the fluorine has an electronegativity of 4, and hydrogen is 2.2. All of the electrons are kind of pulled towards the fluorine. So the electrons would be kind of over here. They would be piling up over here on this side. So this side would be partially negative. This side would be partially positive. So fluorine would have most of it. Electronegativity we use to determine that. A polar bond is a bond between 2 nonmetals. Yes, it always is between 2 nonmetals. That's what we're looking for. So anything that indicates anything else is, so metal and nonmetal is not what we need. A bond between 2 nonmetals, good, in which the bonding electrons are equally shared. This would be covalent, or just evenly shared. So we're going to get rid of that. C, a bond between 2 nonmetals, check, in which the bonding electrons are unequally shared. Yeah, that's what we're looking for, unequally shared electrons. That's what's going to give us a covalent bond where they're unequally shared. Which of the following bonds would be pure covalent? Okay, so we want something that is essentially non-polar. The list of polar bonds versus non-polar bonds. Okay, so non-polar, something bound with itself. So nitrogen, nitrogen, like we have here, carbon, carbon, fluorine, fluorine, any of those are going to be considered non-polar. Also, any combination of carbon or hydrogen, carbon, sulfur, and phosphorus. So carbon, hydrogen, so that what I mean by that is carbon, hydrogen, carbon, sulfur, carbon, phosphorus, hydrogen, sulfur, hydrogen, phosphorus, right? Sulfur, phosphorus. Those, all of those are going to be considered nonpolar. Everything else is considered polar. So nitrogen, nitrogen is going to be considered polar, and we can eliminate the rest of those. All right. Next up, predict the molecular shape of CO2. Okay, so we're going to draw the Lewis structure. And what you're going to end up with, hopefully, is this. So 2 electron groups. That's going to give us something that's linear. Now, is it polar or non-polar? So the electrons are being pulled out towards that oxygen. But the thing is in the middle, we have this positive charge. On the edges, I have this negative charge. But it's not a dipole. These 2 arrows are canceling each other out. If this were a game of tug of war, would that carbon move anywhere? And it wouldn't. So although I have polar arrows, step 1 for getting a polar bond, we're going to say that that thing is, in fact, non-polar. I know that stuff is really hard, but that's what we got. Predict the molecular shape and polarity of CHBr3. So CH, I'm going to draw it how it should be drawn. Again, we always have to draw the Lewis structure first. Br. Do we have polar bonds? Yeah, the carbon-bromine bonds are pulling outward or inward, doesn't really matter, as long as you know that they're polar. And so what we really see is they're all kind of pulling downward. And up top where we have this hydrogen, nothing is pulling. So if this were a game of tug of war, would that move? Yeah, that carbon would be pulled downward. And because that, so this is tetrahedral, so we can eliminate those. And this thing would in fact be polar. Which of the following molecules is polar? So I'm going to let you walk through that and make that decision. Which statement explains why a molecule CH4 is nonpolar? First question is, does CH4 have any polar bonds? And that's, so the bonds between the atoms in CH4 molecular are polar. Actually, that's not true. They're not polar. Bonds, they're ionic. Nope, we don't have any metals. The geometric shape of CH4 distributes charges symmetrically. Yeah, that is true. The geometric shape of CH4 distributes the charge asymmetrically. That's not true. So C would be the correct answer. I don't love this because CH bond is generally not polar, and that's the real reason that it's non-polar, but there we go. All right, so now we're going to start to get into moles. A mole of substance of water, H2O refers to. Okay, so a mole of water. So we have to recognize, if we look at 1 mole of water, within that 1 mole of water, I have what? Well, 1 mole of water, that is 2 moles of hydrogen atoms and 1 mole of oxygen atoms. The idea that 1 molecule, 1 mole of molecules of hydrogen of water contains 2 hydrogens, so 2 hydrogen atoms and 1 oxygen. In addition to this, 1 mole of anything is 6.02 times 10 to the 23rd of H2O molecules. Also, we know that mass and mole are equal. So if we look at the periodic table, we see that water, oxygen weighs 16 grams-ish, and hydrogen weighs 1 gram, but there are 2 of them. So 2 times 1, add those together, the whole thing weighs 18 grams per mole. So also 18 grams of water is going to be equivalent to 1 mole. So all of those, so 1 mole of water, that means 2 moles of hydrogen, 1 mole of oxygen, 6.02 times 10 to the 23rd of the molecules, and 18 grams. All of those are equivalent to each other. So let's see, 12 grams of hydrogen. No, that's actually not true. 6.02 times 10 to the 23rd grams. No, only 18 grams. 6.02 times 10 to the 22nd, or 23rd molecules of H2O. That's true. And then finally, D is correct because actually we have twice as much hydrogen per. Okay. All right. Determine the number of moles of aluminum in 96.7 grams. Whenever we are going from grams to moles or vice versa, we always use molar mass. That's the conversion. So always write the original number, 96.7 grams times fraction. I want grams, and we're going to give labels too. Grams of aluminum on the bottom, moles of aluminum on the top. 1 mole of aluminum. Let me pull out a periodic table. 1 mole of aluminum is 26.982982 grams. Grams cancel. My unit is going to be moles of aluminum. And so now we just do the math. So 96.7 divided by 26.982, 3.58 moles of aluminum, 3.58 moles of aluminum. All right, good. So got a couple pages left. Let's just keep going here. What is the mass of 7 times 10, 7.8 times 10 to the 18th carbon atoms? Okay, so when I'm going from a number, okay, let me do it the other way. Going from a number to mass, we always have to go through moles first. So I know that 6.02 times 10 to the 23rd is equal to 1 mole. And molar mass is what's going to equate grams to moles. So we're always going to start with the original number, 7.80 times 10 to the 18th carbon atoms times fraction. I want carbon atoms on the bottom, and I want to go to moles in the top. 1 mole is 6.02 times 10 to the 23rd. And then one more time, carbon atoms cancels, and I've got moles of carbon. And then finally, moles of carbon to grams of carbon. 12 grams of carbon is equivalent to 1 mole. Just look at the periodic table. And here we go. So now we do the math. So 7.8 times 10 to the 18th. By the way, this looks like a lot less than a mole, so it's less than 12 grams for sure. So right, this is less than a times 10 to the 23rd, right? So we can immediately eliminate A and B because those are gigantic. So we know it's going to be one of those other two. 7.8 times 10 to the 18 divided by 6.02 exp 23, and then times 12. So 1.55 for 1.56 times 10 to the negative 4. So C, 1.5. I got 5.5, but times 10 to the negative 4. None of that matters. That's correct. All right, that's it. Oh, unit is grams of carbon atoms. All right, which sample contains the greatest number of molecules? So we have to do a bunch of conversions here. So we want to, if I want to figure out the number of molecules, really what this is asking is, it is also, we could just say the greatest number of moles, because that's the same thing. Moles and molecules are 1 mole is equivalent to the same number of molecules. So just determine the best number, highest number of moles, and that's how you would do this one. I'm going to kind of roll right through these because I've explained them already. What is the mass of nitrogen in 1 mole of, okay, so mass of nitrogen. So if we're looking at just nitrogen, if I lay this out, I've got 2 nitrogens, I've got 8 hydrogens, I've got 1 carbon, and I've got 3 oxygens in this. So 2 times the 14 grams per mole equals 28 grams of nitrogen. 8 hydrogens at 1 gram per mole gives me 8 grams of hydrogen. 1 carbon at 12 grams per mole is 12 grams of carbon, and 3 oxygens at 16 grams per mole gives us what, 48 grams of oxygen. Altogether, that makes up the total mass of this entire thing. But what we're asked for is how much is how much does the nitrogen weigh? So 28 grams in this structure. Okay, so in this structure, because it has 2 nitrogens that weigh 14 grams per mole. What is the coefficient of water when the following equation is properly balanced with the smallest set of whole numbers? So we can go through this. I always prefer to just go back and forth until they're balanced. So if I look on the left-hand side, I've got 4 aluminums. So I'm going to put a 4 in front here. We can always change these. I've got 4 aluminums. I've got 3 carbons on the left here. And so I'm going to put a 3 in front. So we've got 3 carbons. I don't care about anything else. 4 aluminum still, 3 carbons. And then how many total hydrogens? On the left, I have the 2 hydrogens, and I have hydrogen in both of these structures. So I actually want to do a little bit of math. So in just the aluminum hydroxide, I have 3 hydrogens, but times 4, that gives me 12 hydrogen from this structure, and 4 hydrogens times 3 gives me 12 hydrogens here. So that's a total of 24 hydrogen on this side. So what do I have to put in front of water? I need 12 water molecules in order to get 24 hydrogens. So that takes care of the hydrogen. Have we changed any numbers? No, still 4 aluminum, still 3 carbons. We have 12 hydrogens. How many total oxygens do I have? Again, this one has 3 oxygens per structure, okay? If I ignore the 4, but 3 times 4 gives me 12 oxygens, and I don't have any oxygens on the right. So 12 oxygens, and I already have 12 oxygens. So this thing is balanced. We'll put a 1 out front there, but smallest set of whole numbers for the water. The water has a 12 in front of it. Boom, done. All right. What is the coefficient of H2SO4 when this is properly balanced? Again, we're going to do the same thing. 3 calciums on the left. Now I have 3 calciums on the right. Instead of doing individual atoms, I'm always going to take polyatomics because they're never going to fall apart. They're always going to stay the same. So I've got 2 phosphates here. I'm going to put a 2 out front here. I've got 2 phosphates. So still 3 calciums, still 2 phosphates. I have 2 hydrogens here, and I have 3 in this, but times 2 gives me a total of 6 hydrogens. So I'm going to put a 3 out front there and give myself 6 hydrogens. Start again. 3 calciums on each side still, 2 phosphates on each side, 6 hydrogens, 3 sulfates, 3 sulfates. So we're good. H2SO4 needs a 3 in front of it. Done. All right. Which of the following is classified as? Okay, so if I have, all right. So this is, we're trying to decide what type of reaction. Combination or synthesis reaction, we go from more to fewer. So we're looking for going from combining 2 things together to give us 1, or combining multiple things together to give us 1. That is a synthesis reaction. Decomposition is something is falling apart. So fewer to more. So if I have this one thing and it falls apart into 2 others, that's a decomposition. It's falling apart. A single replacement reaction, I am looking for an element and an element on the other side that is different because the element has singly replaced. Double replacement, we're looking for, it's pretty much the last one. Have they switched partners? This is going to be a combination reaction or a synthesis reaction because we're taking 2 things and combining them together. Same question here. Always look for an element first. If we don't have decomposition, do I have either of these? No, I don't have more to fewer or fewer to more. This side has 1, 2 things. This side has 1, 2 things. Doesn't matter the count, just matters how many different elements are present or molecules. I have fluorine and I go to iodine. So I have elements. We're always looking for elements first. And we go from one element to a different element. That is a single replacement reaction. All right. What is the number of CO2 in 220 grams? Okay, so number of moles. So this is going to be from moles, from grams, actually, grams to moles. So just need the molar mass, do the conversion. What is the mass in grams of 8.3 moles of CO2? This is going from moles to grams. So again, pull out your periodic table, moles to grams conversion. How many grams of oxygen, grams, are in 24 grams of CO2. Okay, so this one's a little bit different. So if I have 24.02 grams of CO2, first thing I always want to do when I'm switching chemicals, we always want to convert to molar mass. And I think this is 44.11 or 44.1 grams. I'm just going to go with that of CO2 per 1 mole of CO2. So right now, if I canceled, my units would be in moles of CO2. What we're looking for is the grams of just oxygen. There's a couple of ways we can do this. Sure, we can do it this way. Um, in 1 mole of CO2, I have 2 moles of oxygen atoms. Okay, moles of CO2 cancel, and that gives me moles of oxygen atoms. And now I take it one step further. I want moles of oxygen to go away. I want grams of oxygen. So 1 mole of oxygen is equivalent to 16 grams in the periodic table. That would cancel. That gives us the right answer. Okay. The other way that I could look at this is I could say, okay, CO2, I have 12 grams per mole plus 2 times 16. So 32, so 44 grams total. Within that, I know that 32 grams, I'm going to divide these up, 32 grams of oxygen, because that's the mass of the oxygen, divided by the 44 grams of CO2 times 100. That's going to give us the percentage of CO2 that is actually percentage of CO2 that's actually oxygen. And then we multiply that percentage by the mass. Okay, so either one of these is going to work. So I'm going to do the first one, 24.02 divided by 44.1, enter, times 2, enter, times 16, enter. So 17.5. So B. All right. Last one. How many atoms of carbon are in 1 gram of C12? Okay, so we're going from grams to carbon atoms. So we're counting. So 1 gram of C12H22O11. This is going to be an annoying one, but here we are. Okay, I'm going to do it down here. All right, times, I always want to go to moles first. 1 mole is equivalent to, well, we have to figure out the molar mass of this entire thing, right? So we have to figure out how much this whole thing weighs. So 12 times 12 plus 22 times 1, because that's the molar mass of hydrogen, plus 11 times 16. And what is the total mass of this thing? So 12 times 12, enter, plus 22, enter, plus so 342, if I did my math correctly, grams per mole. So 342 grams per mole. Okay. Grams cancel, and I'm left with moles of this whole thing. So 1 mole of C12H22O11 is equivalent to, we're looking for grams of carbon or atoms of carbon. So there are 12 moles of carbon atoms in this times fraction. I want moles to go away. I want moles of carbon atoms to remain. 1 mole of carbon atoms is equivalent to 6.02 times 10 to the 23rd carbon atoms. Okay, moles cancel. So 1 divided by 342, enter, times 12, enter, times 6.02 times 10 to the 23rd. Oh, yeah. Yeah. So that's the proper way to do it. I've got to look. It looks like 3, 6, 9, 12, 15, 18, 22. 22, it looks like, is the answer. All right. So that should be it, assuming my math is correct in terms of the mass. But anyway, that's pretty much it. So that's how we do that one. The last video coming soon.